I am Nikita Mishra from Department of Chemistry, Gujarat University. Welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor, Director, UGC HRDC, Gujarat University, and Dr. Dilip Vasawa, Assistant Professor, Refresher Course Coordinator, HRDC, Department of Chemistry, Gujarat University.
The next session is Professor Dr. Navinchandra Shimpi, Department of Chemistry, University of Mumbai. He has more than 12 years of teaching experience in academics and research. His thrust area of research includes nanomaterials and their functionalization, biodegradable polymers and rubber nanocomposites, materials for gas sensing, nanocatalysts and their application in organic transformation reactions, synthesis of carbon nanotubes and its functionalization, nanomaterials for effective degradation of dyes, synthesis of nanofibers and binary materials. He has membership with professional societies as life member of Asian Polymer Association and Indian Science Congress. He has completed 8 research projects funded by high-profile agencies and 1 project is ongoing. 15 MTech students and 7 PhD scholars have been awarded their degree under the supervision of Dr. Shimpi. Additionally, 3 have submitted their PhD thesis and 5 PhDs are ongoing. He has published more than 70 papers in international publications and 2 in national publications. He has presented 40 national and 60 international papers in different symposia and conferences. He has delivered more than 30 invited talks in conferences, workshops, and refresher courses with different subjects. Moreover, he has 2 patents granted and 2 under examination. He has organized more than 10 conferences, seminars, and courses at different levels and played a role as active member, coordinator, convener, treasurer, and secretary. Thank you.
Good morning, friends. Today I am going to deliver a talk on size, morphology, tunable novel nanomaterials as heterogeneous catalysts. Myself, Dr. Navinchandra Gopal Shimpi, Professor, Department of Chemistry, University of Mumbai, Mumbai. So, when we talk about this particular topic, that is the size tunable morphology of nanomaterial, size dependency is very much important in this particular material. And when we talk about the size dependency, before to talk about the size dependency, nanomaterials are known to be dwarf, very small material, and its size been defined in the range 1 nanometer is equals to 10 to the power minus 9 meter. But when we talk about this particular size, the size relates with the dimension of the material, and therefore when at least one dimension should be in the range of 1 to 100 nanometer, that material is called to be a nanomaterial. Composites made from particle of nano-sized ceramic or metal smaller than 100 nanometer can suddenly become much stronger than predicted by existing material. When we talk about the nanomaterials are of two ways. One is atomic scale conversion and second one is a molecular scale conversion. Atomic scale conversion means nanomaterial is control, means size is at the atomic level. And in another case, at molecular scale means size is at the molecular level. For example, when silver nitrate is converted into the silver, when it reduced to silver, and that silver becomes a metal, nanometal, its oxidation state becomes 0. Means silver nitrate converted into silver metal is the atomic scale conversion. And when we talk about the molecular scale conversion, for example, suppose calcium carbonate is there, that calcium carbonate is made with the help of say ammonium bicarbonate. When these two reactants react, they forms the calcium carbonate. Whatever the conversion is there of calcium chloride plus ammonium bicarbonate to calcium carbonate is nothing but the molecular scale conversion. Metals with a so-called grain size of around 10 nanometer are much much as 7 times harder as tougher than their ordinary counterpart with grain size in the micrometer range. When material is converted into the nano size, there will be the drastic change in the properties such as melting point goes on decreasing, boiling point is goes on decreasing, band gap is changing, optical properties are getting changed, electrical properties are getting changed, magnetic properties are getting changed. Even the structure of the material changes with respect to size. When we talk about the nanoscience and nanotechnology, this particular technology was introduced by Nobel laureate Richard Feynman in 1959. But people doesn't have proper idea how this technology will works. But in 1971, Japanese scientist Nario has been developed some nanomaterials, and that nanomaterials have been incorporated into the composite for Toyota Group. They forms the polyamide nanocomposite. And what they found, the properties are getting changed drastically as compared to the pristine material. And from there, people are trying to do the work, but the commercialization is a very important factor. As these materials are economically not viable, therefore people doesn't have look into this particular technology, and they started with again with the normal technology, that is a micro technology. But as day passes, people came to know about the importance of this particular material, and considering that one, nanotechnology has wide applications: textile, cosmetics, drug delivery, defense and security, optical engineering, biotechnology, energy storage, electronics, agriculture and food, metallurgy and materials. These are the vast areas of application where nanoscience and nanotechnology has gaining the fast momentum for the development of better and improved properties of material. The properties of material can be different at nanoscale for two main reasons. First, nanomaterials have a relatively large surface as compared to the micron size material. Means, in short, I like to say here, surface to volume ratio goes on increasing when material is converted micron size to nano size. Nanoparticle can make material chemically reactive and affect their strength or electrical properties. Second main reason is that when material is converted into the nanoscale, quantum effects can begin. Quantum effects can begin means, here we say that material when converted into the nano size, its surface to the volume ratio goes on increasing, and when its surface to the volume ratio goes on increases, its gravitational force gets negligible and electrostatic forces are get dominant. In initial definition, at least one dimension should be 1 to 100 nanometer. And as per the dimensions, nanoscale material are divided into following categories. Zero dimension, when material is in zero dimension, length, breadth and height are confined at a single point. For example, nanodots are there. When material is of one dimension, it has only one parameter, either length or breadth or height. A best example is very thin surface coating. Two dimension, it has only length and breadth. For example, nanowires and nanotube. Three dimension, it has all parameters of length, breadth and height. For example, nanoparticle. As our topic is related with the heterogeneous catalyst, it is very important to know about the catalysis. So, role of the catalyst is to enhance the rate of the reaction by without taking in any part during the reaction, only to enhance the rate of the reaction, and with increasing the rate of the enhancing the rate of the reaction, product yield should be improved. And therefore, on the basis of that, there are the two types of the catalysis. One is a homogeneous catalysis and second one is a heterogeneous catalysis. When we talk about the homogeneous catalysis, reactant and catalyst are in the same phase. Similar like in heterogeneous catalysis, reactants and catalysts are in the same phase. In homogeneous catalysis, difficult to separate, but in heterogeneous catalysis, these catalysts can easily be separated, readily be separated out from the reaction mixture. Difficult to recycle, these heterogeneous catalysts can be readily recycled and regenerated. Regeneration can easily be possible. Homogeneous catalysts are highly selective, but heterogeneous catalysts are lower selectivity, having lower selectivity. In homogeneous catalysis, lowers the rate. In heterogeneous catalysis, very high rates. Homogeneous catalysis can operate under poor magnetic understanding, while heterogeneous catalysis is in a mild condition. Mild condition is sufficient to operate. Several nanomaterials have been employed effectively in various organic transformation reaction as an efficient catalyst due to large surface area. Not only the large surface area, because of the high porosity, this material can be act as an effective catalyst for enhancing the rate of the reaction as well as to enhance the yield of the final product by lowering down the byproduct percent yield, which provides higher catalytic activity. Many reactions can also be possible with the help of the metal nanoparticles, metal nanoparticle like silver, copper, metal oxide like copper sulfate, silver oxide, then copper oxide. Many metal oxides can be possible. With the zinc oxide is also one of the main material which can be seems to be a very effective heterogeneous catalyst. Metal supported nanoparticles, mixed metal nanoparticles, then metal organic frameworks. Many materials can be used as heterogeneous catalysts, and they can operate different reaction like carbonic field reaction, Hake reaction, A3 coupling reaction, Friedel-Crafts alkylation, Suzuki reaction, Bignelli's reaction. These are the many reactions which can be possible with the help of this particular material as a heterogeneous catalyst. In a view of our title of presentation, the first nanoparticle we have used as a heterogeneous catalyst, that is a zinc oxide nanoflowers, for the synthesis of alpha aminophosphonate under solvent free condition. Whatever the reaction we have conducted, the schematic presentation is still showing the reaction, how we have operate this reaction. In this we have taken the reactants, and we incorporate the ultrasonic horn, and that ultrasonic horn is connected with the ultrasonic controller, that is called as a generator. Okay, and at the same time we have added zinc oxide nanoflowers as a catalyst, and we have operated this reaction with the help of this particular process. This is a complete process. Here the formation of the alpha aminophosphonate, there is a aldehyde group, amine group plus phosphonate group is there, and we have added this into the reaction, and they forms alpha aminophosphonate. So this is the material we have used here, that is a zinc oxide as a versatile material. Why this material is called as a versatile? Because it has a large number of other application. This material can be easily been synthesized, availability is easy, synthesis method is very easy. Whatever the percent yield obtained during the reaction, the highest percent yield can be obtained from for the zinc oxide nanoparticle. This material can have different applications, like as a photocatalyst, as in solar cell, as a sensor, as a photodetector for sensing the gas material, leakage gas material, as in the gases, as a gas sensor at room temperature as well as at high temperature also. Because of the vast properties, this material has a unique application, that is n-type semiconductor. This material can be act as a n-type semiconductor, wide band gap, high excited binding energy, non-toxic, easy and cost-effective synthesis. This is the preparation method for the zinc oxide nanoflowers. For that we have used zinc nitrate plus sodium hydroxide. We have changed the concentration of zinc nitrate as well as sodium hydroxide, and according to the change in the concentration we have maintained the pH of the solution at 11, pH 11 we have maintained. And when zinc nitrate and sodium hydroxide react, they form zinc hydroxide, and further zinc hydroxide is reflux at 100 degrees centigrade, they form the zinc oxide nuclei, and they formed zinc oxide nuclei are put for the aging at 150 degrees centigrade, and these nano zinc oxide nuclei are converted into the zinc oxide crystals, and they converted into the nanoflowers. This is the complete mechanism. Simple mechanism is there, from zinc nitrate to sodium hydroxide to zinc hydroxide, and then refluxing at 100 degrees centigrade, then forms the zinc oxide nuclei. Aging at 150 degrees centigrade, there is a growth of the crystals along the C axis, These fibers are these crystals are growing along the c-axis, and they come together and forms the zinc oxide nanoflowers. This is the characterization technique we have used for the characterization of zinc oxide nanoflowers. We have done the XRD. Here is the hexagonal Rusite phase that can be proved from the JCPDS 361451. Material is highly crystalline. That is, the sharp peak itself showing the crystalline material free from impurities, as there is no other peak other than zinc oxide crystal planes. And particle size was calculated with the help of the Scherrer's formula. D is equals to k lambda upon beta cross theta. Here is the major peak, that is 101 is the major peak from which we can calculate the particle size of that particular material. And for verification purpose, whether there is any impurities present or not, we have done the FTIR, and from the FTIR it is being observed that there is no impurity, only the presence of zinc and oxygen peaks are there from 520 centimeter to inverse to 369 centimeter inverse. 369 centimeter inverse suggests for the higher absorption peak of zinc oxide. 520 peak is stretching of zinc oxide. 971 tetrahedral coordination of the zinc. 1459 centimeter inverse is water absorbed on the surface of the crystalline. Somewhere water being get absorbed, and that peaks are come over that particular spectra. This is the UV visible spectra. UV light absorbs at 371 nanometer. That is the indication of formation of very fine size of nanomaterial, and this band gap has been determined with the help of TOS equation, and it found to be 3.12 electron volt. It is near to the actual theoretical value of that particular zinc oxide nanomaterial. And we have determined the thermal stability. Zinc oxide seems to be thermally high stable. It goes more than 800 degrees centigrade, means the material is very stable up to 800 or more than 800 degrees centigrade. This is the X-ray photoelectron full survey spectrum of zinc 2p X-phase spectra and oxygen 1s deconvoluted X-phase spectra of zinc oxide nanoflowers. That is, the oxidation state been determined here, and binding energy for zinc and oxygen is observed from 1021 to 2.8 28 electron volt and 1044.45 electron volt. These are the same images, and the same image itself showing the formation of the nanoflowers. These are the complete nanoflowers are being formed during the synthesis of zinc oxide nanoflowers. And index shows that pure zinc oxide crystals are been there in the loop of that particular material. And particle size analysis was also done, and it found to be 30 nanometer. Carbonyl compound plus alkyl phosphate reacted in presence of 10 mole percent of the zinc oxide nanoflowers as a catalyst. In presence of ultrasound cavitation technique in a solvent free condition, it forms the alpha aminophosphanate. This is the complete mechanism, and in this mechanism, when phosphanate group is forms the complex here, then this alkyl group, amine group, is to that particular amine group, these nanoflowers are attaching to the double bond of that nitrile, and then the reaction proceeds. This attack is from the external side, therefore the separation of nanoflowers becomes very easier one, and once the reaction completed, we have separated out, regenerated this catalyst again, and utilized this catalyst for the next cycle. These are the effect of the reaction parameters. Number of catalysts used by the other researcher, and our group used that zinc oxide nanoflowers. We have verified these zinc oxide nanoflowers from 10 mole percent to 5 mole percent, 15 mole percent, 20 mole percent in solvent free condition, as well as in presence of the solvent. Different solvent we have also used, that is a DCM, water, toluene, water, solvent free condition, even at room temperature or in absence of reflux up to 50 degrees centigrade. And when we compare all these data, previously done by the researchers and our group, that zinc oxide nanoflowers, when we have used 10 mole percent under the solvent free condition in presence of ultrasound cavitation technique or ultrasonic probe, yield of the product is 98%. In this case we have 98%, 98%, but the amount required for of the catalysis, that is 15 mole percent and 20 mole percent. If we get 98% at 10 mole percent, then why should we go for the 15 and 20 extra? Why should we use this extra 5 mole percent and 10 mole percent of the catalyst? Then if the reaction satisfy up to 10 mole percent, then we have concluded here that zinc oxide nanoflowers loading is 10 mole percent is sufficient, and so under solvent free condition in presence of ultrasonic probe, it gives 98%. Therefore a very satisfied results are being obtained at this particular juncture, and therefore we recommend that 10 mole percent is sufficient for the zinc oxide nanoflowers. No solvent is required. Solvent free condition means eco-friendly reaction, and time required for the completion of is very less also. See, 80 minutes, 120 minutes, 120 minutes, 180 minutes is sufficient to conclude that reaction. And some novel alpha aminophosphonate derivative we have synthesized. These are the some novel derivatives we have synthesized with the help of that particular cavigenic field reaction. Comparison of the proposed work with literature available here. So different catalysts: sulfonated polyborate, HFCl4, MgClO4, SiO2, SO3H, nano TiO2 is also being used, copper nanoparticles, zinc oxide nanoparticles, and this is the zinc oxide nanoflowers. Only 10 mole percent is required under solvent free condition. 60 minutes is required. Only 60 minute time is required. Okay, so yield is 98% as compared to others one. If we compare with the other, 90-degree temperature is required, 60-degree, 50-degree room temperature in presence of the solvent. Solvent free can, even it is solvent free nano TiO2, it gives 50 degrees centigrade time required, and time required for the reaction is 4 hours. Here 9 hours is required, here 10 hours is required, but yield is not sufficient. But here only 60 minutes solvent free condition under ultrasound cavitation technique. Reusability study we have done up to fourth cycle we have gone, and when we compare from the first to the fourth cycle, marginal decrement in the product is been observed, and even in the fourth cycle the material does not lose its activity. The same peaks are observed for the zinc oxide nanoflower as whatever we observed in the first in the fresh form of that zinc oxide nanoparticle, and thermally stable up more than at 800 degrees centigrade. Somewhere there is a break of that flowers, but flower uniformity is same throughout the structure. Another scheme we have done, that is expanding application of nickel based metal organic framework in catalysis for the synthesis of 3,4 dihydropyrimidine to 1H1 in Bignell's reaction. Here we have used some organic linkers for the formation of metal organic framework. These are the reactants, and this is the catalyst used, and it gives this particular product, that is a DPHM, that is a 3,4 dihydropyrimidine 2 1H1s, that is a Bignell's reaction is there. What is metal organic framework? This is the metal organic framework. Into this particular metal organic framework, metal ions are at the top of that particular cube, that is a metal ion or the cluster, and these are the squares, these are the rectangle, and the square facet are of organic linker. When organic linkers and metal ion or a cluster comes together, they forms the metal organic framework. And the advantages of the material is high surface area, high porosity, simplicity of processability, stable material. And this material is having the wide application in organic transformation reaction, Friedel-Crapple acylation, Sonaga-Shira coupling, Suzuki coupling, Novel's synthesis, Bignell's reaction, cationic field reaction. PPDCA, that is 4,4-biphenyl dicarboxylic, with the help of the 4,4-biphenyl dicarboxylic seems to be very effective as compared to the BTCA, BDCA and NDCA. When we go for the colorimetric analysis, that is for the measurement of the thermal stability of that particular material, nickel BPDCA, that is a nickel metal organic framework, with the help of the organic linker BPDCA, found to be thermally more stable as compared to the other organic linkers. So when we have done the FTIR, through the FTIR, it has been clearly observed that only the pure form of the nickel metal organic framework being synthesized with the help of the all organic linkers, no impurity is present, uh, and there into adsorption deadsorption spectra suggesting the monodispersed form of that particular surface area and pore dimension of nickel metal organic framework. Here nickel BPDCA shows high surface area, that is 353 meter square gram inverse. Average pore diameter is 33.2, whereas total pore volume centimeter cube gram inverse is been observed 2.902. This is the structures of different organic linkers and how this BPDCA is effective because of this structure, suggesting that there is a biphenyl ring is there, and carboxylic acid are attached to that tip of each biphenyl ring. Here the fuse ring is there, here is only single phenyl ring is there, here again single phenyl ring is there, and because of the structural stability of that BPDCA, this BPDCA gives more stable, more high surface area with average very impressive pore diameter with total pore volume of nickel BPDCA metal organic framework. These are the same morphology, and even the same morphology is showing that very uniform size of the nickel metal organic framework being formed with the help of the BPDCA with uniform dispersion, no cluster is there, very uniform size with a uniform thickness. Here is the Bignelli's reaction, that is urea or thiourea we have used. Here X can be replaced with the help of the oxygen urea, and S will be the thiourea plus aldehyde plus your 1,3-dicarbonyl compound. And when we add the catalyst and process the reaction at under solvent free condition, it gives the DHPMS, that is a 3,4-dihydropyrimidine 2,1H ones or thiones. That material is called as a Bignelli's adduct. And these are the biological activity of this particular DHPMS, that is a anti-neoplastic, anthelmintic, uh, parkinsonism, antibacterial, antifungal, vasodilator, liver disorder. This material can be used in this application, very large application for this particular material. Now, effect of reaction parameter. When we conduct any organic reaction with the help of different catalysts, it is very important to understand their this one, that is a reaction parameter, effect of the reaction parameter on the final yield of the product. And as mentioned, we have conducted this reaction in presence of the catalyst by varying the amount of the catalyst in milligram, by changing the solvent or under solvent free condition, different condition in presence of ultrasound technique, ultrasound cavitation technique, or at rising the temperature, or even in ultrasonic bath. Accordingly, we observe that we have conducted this reaction in presence of nickel metal organic framework with the help of a BPDCA as organic linker. We use the catalyst amount 20 milligram constant, and only changing the solvent methanol, ethanol, acrylonitrile water, and under solvent free condition. And another condition we have used, that is under ultrasound cavitation technique. We observe that in case of in nickel BPDCA, under solvent free condition in presence of ultrasound cavitation technique, 89% yield is obtained, uh, whereas in the presence of different solvent, methanol, ethanol, acrylonitrile water, the percentage yield is very less, it is less than 75%. Again, when we compare this NiBPDCA with other catalysts, if no catalyst being used, the reaction cannot be proceed without catalyst. So Again, we have tried to go with 10 more milligram and 30 milligram of nickel BPDCA. We have increased the amount of the catalyst, and we observe that uh, at 10 milligram, uh, at 10 milligram, 77% is being observed, while at 30 milligram of loading of nickel BPDCA, 89% is being observed, and therefore we concluded here 20 milligram is sufficient to enhance the percent yield of the product. And again, when we compare with other organic linkers, the percentage yield is very less as compared to BPDCA. So synthesis of DHMPS using nickel BPDCA. This is the complete reaction in presence of this catalyst, solvent-free condition under ultrasound cavitation technique. And we have changed the alkyl group here. Upon changing the alkyl group, we observe that 4-methoxybenzaldehyde and 2,5-dimethoxybenzaldehyde and 3,4,5-trimethoxybenzaldehyde gives the higher yield, that is 96, 96 and 97. And this material is more selective for 3,4,5-trimethoxybenzaldehyde, which gives the highest, that is a 97% yield. This is the selectivity study we have done for the alkyl group. Upon changing this alkyl group of the aldehyde here, if we change the R, then we get this particular group. Comparison excellence of nickel BPDCA with some reported metal organic framework. This is the time required is 60 minutes. Here is 2 hours, 4 hours. Here temperature is very high. No temperature under with the help of the ultrasound cavitation technique in solvent-free condition. We have done 60 minutes, 89% yield. And when we go for the recyclability study, up to 5th cycle, the percent yield of the product goes reduced drastically, and therefore the reason behind is that the material loses its porosity up to 5th cycle, means it starts to lose its porosity from 3, 4 and 5th cycle. Fiber is a natural fiber are vegetable, animal, wood, mineral and biological fiber or synthetic fiber. Synthetic fiber are semi-crystalline, synthetic, carbon metallic, silicon carbide, glass and polymer substance that is significantly longer than its width. Fiber are often used in the manufacturing of other material. The strongest engineering material often incorporate fibers, for example carbon fiber and ultra high molecular weight polythene. Why nanofibers? When we talk about the fibers, fiber strength is very high. There are very much available fibers are there, synthetic fiber and natural fibers, as I mentioned earlier. When we talk about the nanofibers is having large specific surface area. Surface to volume ratio is very high as compared to the normal nanomaterial. Porosity is very high, highly porous, because fibers are waved each like this, therefore high porosity. Smaller pore size. When we talk of the porosity, whatever the pores are there into that particular structure, the pore size is very small, and specifically diameter is in the range of 52,000 nanometer. Here materials are used, polymer solution or melt. We need to prepare the solution of the polymer, or we need to melt the polymer material first and then put into the drawing technique. And more than 30 polymers including polyethylene oxide, DNA, polyaramides and polyaniline have been electrospun with the help of the electrospinning technique. When we talk about the application of the nanofibers, these nanofibers are being used in various applications depending upon the morphology of that particular fiber. Porous, branch, pivot, wire in tube, multi-wall, multi-channel, non-cylindrical, necklace-like structure, and like this. Surface multi-level structures are there. Inner multi-level structure are, this is the inner multi-level and this is the surface. This is the surface multi-level structure, and this is the inner multi-level structure. This structure is called as the inner multi-layer. Okay, one fiber is there, into that fiber another 3 fibers, multi-channel, another fibers are there, therefore it is called as a multi-channel. This multi-wall, and this is wire in a tube. This is the tube, and in that tube one wire will be there, therefore it is called and pivot like. This is the p-pod like structure. And when considering these different structures of that particular material, various applications are there: sensors in energy storage, catalysis, biomedicine, cell adhesion, tissue engineering, filtration, and as a microreactor. Why electrospinning? This is the comparison of the various processing method for the drawing of the polymer nanofibers. Different techniques are there: drawing method, template synthesis, phase separation, self assembly, and this is the electrospinning technique which are being used right now for the drawing of the nanofibers. Why this technique? Laboratory technique is there, potential for industrial processing also, repeatability is possible. Repeatability is possible in every case, but when we talk about the advantages: simple process, cost effective, a large variety of polymer can be electrospun. Here are some limitations are there for drawing the polymers, but to use the polymer, long continuous nanofiber can be produced. Production of aligned nanofiber is also feasible. Here aligned fiber is not possible. All polymers cannot be used in this process. Some modification is required, and then we can able to draw the fiber with the help of the drawing, template synthesis, phase separation, and self assembly. And when we talk of the limitation, these materials, these techniques is having limitation. 1 2 3 4 techniques is having limitation, but here is no limitation. Only we need to control the reaction processing condition. Once we control the reaction processing condition, fibers can be drawn very uniform with uniform thickness, and a long fiber can also be possible. This is the electrospinning setup. In the electrospinning setup, this is the schematic form. Here we use the high voltage power supply controller. That connectors are being connected to the needle, and solution is being put into the syringe. There is a compressor which pushes the pumping the solution through the needle. Then fibers are collected over the collector plate. It is a conductive substrate is there. Over that conductive substrate, nanofibers can be collected, and they forms the Taylor cone system. When solution comes from the needle, there is a formation of the Taylor cone. That cone is called as a Taylor cone, which is a positively charged, and because of that, the conductive substrate is essential for the collection of the fiber. When high voltage is applied, high voltage from 10 to 30 kilovolt, okay, more than 10, not less than 10, and up to 30 kilovolt is been possible, that a high voltage power supply is required. When voltage is applied, whatever the liquid is there into this syringe, it becomes charged, and electrostatic repulsion counterparts the surface tension, and the droplet is get stretched. These droplets are getting stretched and drawn over the collector plate. At critical point, liquid erupts from the surface. A conductive substrate, normally grounded, which serves as a collector for the electrospun nanofiber. Important parameters: solution properties. These are the important parameters for solution properties, such as viscosity. Moderate viscosity is required, and if the viscosity is moderate, elasticity is been balanced. Conductivity, surface tension, which in turn are affected by molecular weight and molecular weight distribution. Processing condition, such as electrical field, flow rate, distance between the needle and the collector plate, take-up rate. Ambient condition, temperature, RH of the environment, type of atmosphere, and atmospheric pressure. Now, these are the different parameters which are very important when we draw the nanofiber with the help of the electrospinning technique. When optimizing the parameters like concentration of the solution, what will be the structure of the nanofiber will be there. That picture suggesting at different molecular weight or at viscosity rate. When viscosity is 10 weight percent, the fiber obtained is in between 200 to 400 nanometer. If we enhance the viscosity 12 weight percent, it goes to 700 to 800 nanometer, and again if we increase up to 15 weight percent, it gives 1 micrometer. Therefore, it has been suggested that the mild viscosity, moderate viscosity is an important parameter that will give a very lower size of the nanofiber, and it is suggested that 10 weight percent so viscosity of the solution is 10 weight percent is sufficient to draw the fiber of 200 to 400 nanometer. When we apply the voltage, upon applying the voltage, what will be the change in the fiber size? These are the field emission scanning electron microscopy of PAN nanofiber at different applied voltage. 15 kilovolt gives 344 nanometer, 20 kilovolt gives 323, and 25 kilovolt gives 331. Not too low or not too high. So 20 kilovolt is the optimized voltage where the fiber can be drawn in between 323 nanometer. If we again balance the concentration or viscosity of the solution and moderate the temperature again, means if we go the range of in between 15 to 20 kilovolt, again we can have a very controlled size of fiber can be possible. And when we talk about the distance between the tip and the collector plate, if we go for the 20 centimeter, it gives 368 nanometer size of the fiber. It means distance should be, travel distance should be the maximum, not to maximum, but it should be the moderate one, it should be the maximum one. And then fibers are formed very fine up to 368 nanometer. Now we go with the actual fabrication and characterization of PAN AGG C3 hybrid nanofiber, that is a polyacrylonitrile silver grafted carbon nitrate hybrid nanofibers. So this is the methodology for the fabrication of the PAN AGG C3N4 hybrid nanofibers. We synthesize initially grafted carbon nitrate, that is a GC3N4 nanoparticles, with the help of the urea by pyrolyzing at 50 degrees centigrade and at ambient pressure gives the grafted C3N4 nanoparticles. We prepare the solution of bulk GC3N4, sonicate it, and we disperse into the solution uniformly with the help of the ultrasonic probe. We prepare the solution of silver nitrate, mix both the solution, and upon mixing this solution, or we can separately synthesize silver nanoparticle but with the help of AgNO3 plus Ag plus NO3 2 minus NO3 minus. What happened? Again there is the reduction is taking place, Ag plus converted into Ag0. We stabilize that silver nanoparticle for 24 hours, and once we get stabilized, we mix both the solution and sonicate it again, and there is a formation of AgGC3N4 nanoparticles. The solution of AgGC3N4 nanoparticles is being incorporated into the solution of polyacrylonitrile viscous solution of the polymer, and then put the solution into the searing, and we draw the fiber with the help of the electrospinning technique. This is the fiber which we have drawn with the help of the electrospinning. This is the XRD and FTIR. XRD and FTIR is self-suggesting that there is a formation of pure form of polyacrylonitrile silver grafted carbon nitride nanofiber. Here is the XRD of AGGC3N4 PAN nanofiber and PAN AGGC3N4 nanofiber. Both the peaks are combined into this single XRD peak, itself suggesting that formation of PAN AGGC3N4 nanofibers are there. While in case of the FTIR, complete peaks functional groups are present, that is 2935, 2246.5, 1457.8, that suggesting the formation of PAN AGGC3N4 nanofiber. When we verify the stability, thermal stability, it has been observed that PAN AGG3N4 is thermally more stable as compared to the PAN and as compared to AGG3N4 nanoparticles. Even we have investigated the thermal stability of silver nanoparticle and grafted C3N4 nanoparticle. It is found that PAN AGG3N4 nanofibers are thermally more stable as compared to PAN AGG3N4 silver nanoparticle and GC3N4 nanoparticles. This is the same image that shows that the complete formation of this particular fiber is there. This is the same index mapping of PAN AGG3N4, uniform dispersion of silver grafted carbon nitride over the surface of PAN nanofiber. These are the XPS study which gives the oxidation state, presence of the oxidation state of AGG3N4 over the surface of the polyacrylonitrile fiber. This is the there is a complete uniform dispersion with uniform size of decoration is being taken place. Decoration is being taken place. EGG C3 and 4 nanofiber nanoparticles over the surface of polyacrylonitrile nanofibers. Now we utilize this particular nanofiber for the different as a heterogeneous catalyst for the different reaction, oxidation reaction, selective oxidation of styrene, CH2 bonded molecule and benzene. This is a schematic presentation. We have drawn the nanofiber here, the nanofiber of a pan AGGC3 and 4 nanoparticle. These are the same image of that particular nanofiber, and these are the oxidation reaction of selective oxidation of styrene, CH2 bonded molecule and benzene. They forms this product. Which one is a major, which one is a minor, which one is a selective one, that is being determined with the help of this particular nanofiber. Now catalytic evaluation of pan AGGC3 and 4 nanofiber towards the styrene. Here is the styrene under light, and as a catalyst, that is a pan AGGC3 and 4 nanofiber, H2O2 as oxidizing agent, and they forms 1, 2, 3, 4 products. First product is a styrene oxide. Okay. Second one is a benzaldehyde. Third one is a benzoic acid. Fourth one is a that is a phenylacetaldehyde, or we say it is a phenylacetaldehyde. Okay. If we look into this sequence of the product, that is a pan AGGC3 and 4 in presence of methyl cyanide. Time required for the reaction to complete the reaction is 16 hours, and it gives 98% conversion. And in this 98% conversion, styrene oxide forms 60%, benzaldehyde 32%, phenyl acetaldehyde 7%, while benzoic acid is only 1%. Means major is sulfonyl oxide. Styrene oxide is the major one. And when we compare this particular nanofiber with a different what we call, that is a solvent, the in different solvent condition, the percent yield is get reduced. That is, and even in the selectivity studies, styrene oxide formation is very less. Here the benzaldehyde is very high, but it is selective for the styrene oxide. Catalytic screening and the reaction optimization. We have done the screening and optimization of the reaction by changing the alkyl group. We found that for CH3 and phenyl, when we put R as a pH and CH3 here, 98% conversion is there. But when we compare with the selectivity study, styrene oxide is more in case of 4CH3 group. That is, this is more selective for this particular alkyl group. Ethyl benzene is there, and that ethyl benzene is converted into this particular product, that is acetophenone, and oxidizing agent is again H2O2, catalyst is same. And when we talk about the same solvent condition, reaction time required is 12 hours, and completion of the reaction is 90, conversion is 98%. Acetophenone is pure acetophenone is formed, no side product is there. We have gone with the different reactant. We forms the different product. Conversion is there and selectivity is there. Very highly selective, very specific selective for this particular group, with high percent yield of the product. Very impressive material, as it has a very fine size with uniform length along with high porosity. Material are very impressive in every part of the reaction, that is in ethyl benzene, in styrene oxidation, and in CH oxidation of benzene. Now we look into the CH oxidation of benzene. So here benzene, when react, it gives phenol, and again same condition, pan AGGC3 and 4 in presence of solvent as a methyl cyanide. 30-minute time we require, 90%, 99% conversion of phenol is there. This is the scalability of the reaction. Gram scale reaction was conducted using 0.228 gram of benzene. The scale up reaction afforded the phenol with 86% yield after 30 minutes. means scalability of pan AgG3 towards the CH oxidation of benzene we have done, means 3 millimole to 86% of the product is obtained. When we go with the recyclability study from first to eighth cycle, marginal decrease in the percentile of the product. And when we have done the ICP AES study, it is observed that silver concentration before reaction, when before start the reaction, it is 4.556, but after 8th cycle, at every cycle we have tested, silver concentration of the reaction is 4.55%, only 0.01% leaching of the silver from the surface of the particle is being observed. And we have done the morphology, there is no any change in the structure of the pan AgG3N4 nanofiber at all, only small disturbance, small leaching out of that silver particle from the surface. Other than the material is as such, even we can use further, only the nominal decrease in the percentile of the product being observed. Then fabrication of pan AgG hybrid nanofiber. Initially we synthesize graphene oxide with the help of the graphite using Humer's method. That graphene oxide is formed, and meanwhile we synthesize silver nanoparticle with the help of the silver nitrate, and they forms the silver nanoparticle, and both the solution we combine and form with the help of the sodium borohydrate as a reducing agent. There is a formation of silver graphene nanosheet. This sheet is called as a AgG, means silver graphene nanosheet. And solution of polymer pan with solution of silver graphene sheet combined together and put this solution into the syringe, and we draw the fibers of polyacrylonitrile silver graphene nanofibers. Characterization we have, this is the characterization XRD and XTI study. Presence of both the peaks in pan AgG, means pan silver graphene sheet is self-suggesting the formation of the nanofiber. We compare this with pan and AgG, and it's been observed that there is a formation of this nanofiber. The presence of the functional group showing the formation of pan AgG nanofibers. We have done the FECM study, and this decoration of silver graphene nanosheet over the surface of the fiber. We have done the X-phase study also, and convoluted deconvoluted spectra is being put into the insect, and the presence of the binding energy for silver is 373, while with silver pan combination it goes to 367. This is the transmission electron microscopy, very highly porous. If you look into this particular patch, there is a decoration of silver graphene sheet over the surface of the pan nanofiber. These are the pan, these are the AgG nanoparticles over the surface, and a very highly porous material, means they are completely decorated or embedded structure inside the thermal properties. Thermally high stable as compared to the pan and AgG nanosheets. Pan AgG nanofibers having high melting point 360 degrees centigrade, whereas pan is 288 degrees centigrade, and we have recorded for AgG also it is nearly 288 degrees centigrade or 293 degrees centigrade, like this. We have done the mechanical property. We have studied the mechanical property of this. Tensile strength at 50% is more, very highly strengthening material. Elongation at break is more at 50%, means from 0 to 58% loading. Tensile strength, elongation at break, Young's modulus and hardness goes on increasing because of uniform dispersion of that particular material into the matrix, and therefore mechanical property seems to be very impressive. Now, pan AgG graphene nanofiber as a photocatalyst under radiation. Photocatalyst. What is meant by photocatalyst? Is a substance uses light energy to facilitate chemical reaction, where in presence of light and water, photocatalyst creates strong oxidizing agent and electronic holes to break down the organic matter to carbon dioxide and water. Because of the use of the nano form of the photocatalyst, there is an increase in the band gap, that is a formation of the holes from valence band to the formation of electrons in the conduction band. Highly excited recombination is taking place. Excitation is taking place. When visible light is put over the surface of the photocatalyst, and when this paranitrophenol, when goes degradation in presence of copper sulfate as a photocatalyst, there is a combination of holes with recombination of the electron reduction, that is a degradation product is formed. Oxidation and reduction is taking place, and complete separation of the mineralization is being taking place. It is been assumed that when degradation is taking place, split of the molecule is taking place and mineralization is being possible, and that mineralization can be verified with the help of the LCMS. Chlorophyll is the natural photocatalyst, is the best example, which captures the sunlight to turn water and CO2 into oxygen and glucose. When sunlight falls over the surface of the leaf, carbon dioxide plus water undergoes to form glucose and oxygen. Application of the photocatalyst. What are the applications? It is acting as a sterilizing. It gives the sterilizing effect, deodorizing effect, air purifying effect, anti-fogging and self-cleaning, water purification and dye degradation. So these are the best. So this is the best slide. 2 billion people belonging to 60 countries of the world are drying out for water. By the year 2050, the figure may go up to 7 billion. When a crow is searching for the water, he finds the water. The water is at the bottom of that particular pot. He used to throw, for getting the water, he used to throw the stone inside the pot. Because of the weight of the weight of that particular stones, water is get lifted out and he take the water. He feel his thirst by taking the water. Then as time passes, he doesn't use to throw the stone inside the pot. He directly uses the straw to lift the water. Then again, instead of putting the straw inside the water, he put the motor here to lift out the water and he removes his thrust. But if no water is there inside this particular pot, what we will do? That is the big question. And therefore we have to search for the another option, that whatever the wastewater is there, whatever the sea water is there, we need to purify that water and use for the drinking purpose. And therefore these are the tremendous amount of the water which goes out into the uh, as a wastewater, and very highly hazardous organic dyes are there inside that particular water, and we need to remove these organic matters from the water and make that water for the purpose of not only not for the drinking purpose but for the other washing purposes, washing the clothes, washing the tiles and tones like this. We can use this particular. But if you talk for presence of the catalyst from 0 minute to 75 minute, and here we go from 0 to 90 minute, very high degradation is taking place for both. We have done the kinetic study for methylene blue as well as methyl orange. It finds that pseudo unipolar first order reaction. This is the degradation mechanism. Very elaborative, very descriptive mechanism is there. Mineralization or mineralized product is formed after degradation. That is been assumption, not only assumption but the realistic. It comes from the LCMS study. Reusability study we have done. That is number of times, that is a fifth. We have gone up to fifth cycle. For methylene blue it is 91% degradation. For methyl orange it goes to 84% degradation. With respect to the different organic link quenchers, without quencher 88%, 82%. In case of IPA, or when we compare in case of the other quenchers, that is 68%, 66% degradation is there. We have done the TOC removal study also for methylene blue and methyl orange also. That is in case of silver graphene sheet 75%, pan 21%, pan AGG is 86%. whereas for methyl orange it is 80%. Reusability study we have done, that is with help of the XRD and FACM, that is no change in the structure at all, as the peak of XRD remains same, as same study itself showing that the decoration of silver graphene sheet remains as such over the surface of the pan. No change in the thickness, no change in the porosity of the particle, only minor change is there over the structure of the particle. We have done the FTIR study, degraded MB, that is a methylene blue, pure methylene blue. The degradation itself, this change in the structure nature of the peak itself suggesting that methylene blue is degraded. Degraded methyl orange and without degraded methyl orange, before degradation and after degradation, it has been observed that removal of the additional prick from the pure methyl orange in case of the degrading methyl orange itself suggesting that the material is getting degraded and the effective degradation is being happen with the help of the pan silver graphene sheet nanofibers. When we compare this particular study with the other nanofibers, we observe that pan AGZ nanofiber in case of methylene blue at 75 minutes in presence of solar shows a very effective degradation. Degradation is taking place in 75 minutes only. Pan AGZ nanofiber for methyl orange gives 90 minutes. If we compare with the other, it takes 6 hours, 180, 170, 180, 480 minutes, 5 hours, 7 hours, like that. Means our work, whatever the work we have performed, that work seems to be very capable for degrading the methylene blue and methyl orange, and definitely in coming time we are able to sort out the uh, whatever the requirement or whatever the way to require the water from the different sources, that can be easily solved with the help of the nanofibers as a photocatalyst for the degradation of the organic dyes. Concluding remarks: the material synthesized using various synthesis method as well as technique shows monodisperse and uniform size of nanomaterials and nanofiber. The as synthesized nanoparticles and nanofibers shows enhanced photocatalytic activity. The photocatalytic activity continues till 5th to 8th cycle with impressive yield of the product. The degradation of hazardous organic dyes using nanofiber found to be very effective. I thank you to my research group in the University of Mumbai Department of Chemistry. Special thanks to the research group which I was guided when I was in Jalgaon University. Thank you. Thank you very much for your attention. If any questions, please ask.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.